So now that we understand one capacitor, let's go ahead and see what happens when we have a combination of multiple capacitors. We're going to specifically look at the case where our combination is going to be either in what we call series or in parallel. So let's go ahead and start with the idea of parallel first and introduce what that means. So remember that we're going to have some voltage source. This could be a voltage of a battery or a power supply. So I'm going to call that the voltage, the delta V across my voltage source. So that's the total supplied voltage. Remember that that's essentially creating a hill between our positive side and our negative side. And that symbol is just the symbol for a battery or a power supply. And so then what we're going to do when we talk about parallel combination is I'm going to go ahead and stick in a capacitor. Remember the capacitor, just the two parallel plates. So I'm going to call that C1 and then complete my circuit. And so a parallel circuit combination is such that you have a full path through one of the capacitors or through the loop with the capacitor without having to pass through the other capacitors. So if I then draw another capacitor here, say C2, and we can see that we connect these points where there's a junction and it changes which loop you can go through, then what we say here is that C1 is in parallel with C2. We might write this as C1 parallel to C2, just to keep our notation straightforward. We call these points of a choice in the path a node. So that's like a junction where you can choose which path you go through. So we can see that we have a complete closed path with C1. We have a separate closed path which would traverse C2 without passing C1. So that's what defines it as parallel. So if we have this parallel combination, and I'm going to redraw it so that I don't draw too much on just one diagram here, we are going to then have our C1 and we'll have C2. We want to remember what we know about potential. So remember, potential is making a hill, right? So this is a hill, and this is our valley, right? So we can then remember that it's creating a voltage drop, but it's creating a voltage drop across our circuit elements. So for each part of a wire that has not had any circuit element in the middle of it, in this case, the capacitor, so all the points on this wire are the same conducting surface with nothing in the way. So they are all at the same potential. So when we visualize a circuit like this, we want to see that every part of this positive voltage that I go through, I'm not passing any circuit element, there's nothing in the way. This whole part is all at going to be my voltage plus of the power supply. So we want to visualize that voltage, that hill. They're all at the top of the hill. And then on the other side, we can make the same case. This is our minus portion. These are all the same conductors, same conducting surface as well, with nothing in the way. And so all of these points, no matter where, are at our V minus. So if we visualize our circuit that way, we see an important result, which is that when in parallel, the delta V across each branch is the same. So, and in this case, it's equal to the voltage across the battery. Now, things might get more complicated. I'll give an example of that in a second. But across each branch, I can add as many branches as I want, and it might look different. I might have ones that look like this. And you can see that that's now a different way of looking at 3 in parallel. I'm going to have every branch is going to have the same side of the potential on the left side and then a different potential on the right side. And these are all going to have the same delta V across them. So visualizing the potential first is going to be the easiest way to start analyzing circuits, first with capacitors and then next module when we add in resistors. So really picturing that, that voltage will allow us to understand some of the rules. And so that's our parallel configuration and talking about the voltage in the parallel configuration. So I'm going to box that result. And then we can then talk about what is the charge on each capacitor. So if we think about it in this way, I'm going to again draw, there's going to be a lot of circuits that I draw in these video notes. So if I go ahead and I just start with my 2 capacitors again, just to keep it simple. Then if I imagine what I'm having is the flow of charge, right? I'm having the flow of charge, so I'm essentially having some electrons flow around this circuit, and they flow through the power supply, and they gain their energy as they go through the power supply. So it's essentially them like going down the hill, or in the electron case, they're going up the hill and gaining their energy in that case. And so they're going to be gaining the energy and going around, but they get to the junction and we know that the charges have to split at this node. They can't go both ways. So what's going to happen is that the total charge, if I call this first capacitor C1 and C2, then what I see is that the total charge stored on C1 and C2 is just simply going to be equal to the charge on C1 plus the charge on C2, and that would be equal to my Q total. Now that might sound like a really obvious result, and hopefully it feels that way. And if it feels that way right now, remember that. So as we start adding in kind of more layers and more different scenarios, remember that we can fall back on kind of like our common sense in order to think about what some of these rules are. So my charges are going to add because they have a choice about splitting at this junction. And so I'm going to then end up with some charge on C1 based on its capacitance and some charge on C2 based on its capacitance. And the total charge that I can store is going to be the sum of both of those. Remember that we have this very important relationship, which is that capacitance is charge per volts. So if they all have the same delta V across them, then they're going to have different charges that they can hold based on their capacitance. I like to think about this as the capacitance of some capacitor, say capacitor I, will be equal to the charge that capacitor stores divided by the delta V across that capacitor. And so we can then, find the Q across a capacitor if you know your delta V across it and you know your capacitance. And then you could get your total charge. So that's our basics for our parallel combination. And then the last thing that we're going to do before we move on to series is to come up with a goal of trying to talk about an equivalent capacitance of this situation. So let's say again, redrawing my 2 capacitors in parallel, C1 and C2. Now I'm going to come up with a goal where I want to make a so-called equivalent circuit with some equivalent capacitance. That is there something that to the power supply, if I keep the same power supply delta V sub S, that to this power supply is going to look the same. So if I have my power supply here, delta Vs, is there a circuit I can draw that just has a single capacitor, which we're going to call CEQ for the equivalent capacitance, that looks the same as this top circuit? And if we think about it, we can use these previous results knowing that the total charge adds in this case, right? So we can say that, you know, if CEQ is going to be equal to my equivalent charge stored over the delta V that they see. Well, remember that they see the same delta V in parallel, and the total charge, as we just talked about, would be Q1 plus Q2. So that would be Q1 plus Q2 over delta V, in this case delta V of the battery, which is also my delta V of the source. So I'm going to kind of probably go back and forth between calling it delta V of the battery, delta V of the source. You'll see both as we go through. And so then we can see that that's essentially going to be equal to Q1 over delta V of the battery, which is also equal to delta V1, plus Q2 over delta V2, since again they have the same delta V across both of them. So they both have that same delta V. And so then that's actually just equal to C1 plus C2. So we have this really nice result that in parallel, capacitances add. So CEQ, if I could keep adding ones, I would end up with the same result, C1 plus C2, all the way to however many I have. And this is a key result. You will find it on your equation sheet, and we will use it to analyze circuits. Okay, so now let's move on to a series combination. So this again was for parallel. So I'll put that here, parallel. And so now let's go ahead and talk about series. So first let's talk about what series means. And you might have a guess at this point. So we have a delta V of our battery, and then I'm going to put a capacitor in the loop. And then instead of making a whole nother branch, I'm going to give no choice but to go through both capacitors. So now my one single loop is going to have both capacitors in that space. So this is what we mean by series. Note that this can be drawn different ways. This is the same as the following. So if I draw one of the capacitors here, and then I come down and I draw another capacitor here, that's actually the same circuit. This is still the same circuit. I still have to go through one and then go through the other. The lengths and shapes of the wires in between the elements doesn't matter. There are no nodes in this circuit. So I'm going to go ahead and label these C1 and C2. So C1 and C2. And we can then start to talk about these same ideas. We want to talk about the potential to start. So if we have our positive side of the potential, this whole wire, and I'll do it for both of the diagrams so you can kind of visualize it. This whole wire here is going to be at the same potential. This is all at V plus. This is all at V plus of the battery. We can then look at the minus side of the battery over here. And so then the minus side of the battery is all going to be at V minus. So that's all at V minus. So now that voltage drop isn't across each individual one. The voltage drop of the battery is across the total of the two of them. So that's the delta V of the battery. So each individual one doesn't get the total voltage drop from the battery. They don't get the full hill. They're both sharing the hill. And so we have to kind of introduce a new voltage that's kind of in the middle here. So that's going to be between, and it depends on the capacitances, it's going to be between V plus and V minus. It's like part way on this hill that we get this other value of potential. But what we can say is that the voltage drop across C1, so the voltage drop across C1, delta V1, and then the voltage drop across C2, delta V2, those will have to add to the total. So this is a key result, which is that in series, our potentials, our voltage drops, are going to add. Unlike in parallel, right, we saw that it was the same delta V for parallel across them. And then here we're seeing that instead they have different delta V's, and then we see that the delta V total, which is the delta V of the battery, which is the delta V of the source, so I'm just calling it a lot of different things, is going to be equal to the voltage drop across 1 plus the voltage drop across 2. And then if I have more, I could add those in as well. So this is a key result for series. And again, hopefully you're just seeing these results by visualizing the voltage. So they're not things to be memorized, they're things to be really understood in your core. And so if in series, if the potentials add, then what we're going to talk about now is what happens to the charges on these capacitors. Well, if we think about it in terms of the electrons, so let me just scroll to a new page. If I say here, what about the charge? And you guessed it, I'm going to draw another diagram, and I'll keep this one, which is sometimes a little bit less obvious of a series one, but it's still just this single loop. There are no nodes. And so there's going to be no paths, no break-offs for the electrons. So my electrons that come around are going to have to all travel the same path. Now with capacitors, they don't actually jump across the gap. So let's imagine what's going to happen. So if I put a positives here, right, then what's going to happen, right, is that if I put a positive here and I'm going to end up with a bunch of positives there, my electrons, right, because all of this has to be the same potential, my electrons are then going to come from the negative side and they're going to go collect down here. And so then I have some charge on this capacitor, which I'll just say is like this side is plus Q. And remember, capacitors in steady state are going to have equally charged but opposite plates, which means that what's going to happen is that I'm going to have this plus plate at the top and a minus plate on the bottom. Then in this inside conductor that doesn't really touch the power supply, its charges are going to separate. Its electrons are going to go start collecting at that plate, and that means that they're running away from this bottom plate, and we end up with this separation of charge even on that wire where the electrons are kind of stuck. They can't really move anywhere, they don't have any nodes, but they can still separate and kind of match the charges on these two capacitors. And so what's going to happen then is because of all of this, if I call this top one C1 and this bottom one C2, then I'm going to have Q1 and Q2. And because of equilibrium, all these charges are going to have to kind of orient themselves. We're going to need the charge on each of them to be the same. So Q1 is going to be equal to Q2. Each capacitor in series has the same charge. Which is a really great result. So, so that's going to be in series. And then the last thing we want to do is to make an equivalent capacitance. So an equivalent capacitance in series, we can go through the same discussion that we did before, that we want to have essentially equivalent capacitance to this system above. And we want to have that the equivalent capacitance is equal to the equivalent charge that's stored. And that's now what's the same for all. And now that's going to be over my voltage, my delta V equivalent, which is the delta V of the battery. And this is what adds. Then we get this result when we work through the math of that. We get that CEQ in series is going to be equal, and I'm actually going to write it this way. I'll write 1 over CEQ equals 1 over C1 plus 1 over C2 plus etc. And that's again going to be our series equivalent capacitance. Okay, so in the next video, we're going to discuss how we use these series and parallel combinations to analyze different circuits.